Hello students, today we are going to study a very important topic, simple harmonic motion. This is a very important topic for IIT JEE, and after we will have some understanding, then we will do a lot of problems. So let us start with a mass spring system. So mass M is attached with a spring, and this system is kept on a frictionless table. There are no forces acting on the mass and there is no energy loss from the system, and this is kept in an unstretched position. So from the unstretched position, here I will assume my origin, okay, and this is my mean position. Now if I pull my mass through distance x, this mass will experience some force, and this force will be directed towards the mean position. Now if I press this mass with displacement x, then there will be some force again towards the mean position. The spring will try to stretch out. If I pull this mass with double the distance, then this mass will experience more force. If I keep on increasing this x, the force will also increase. So I can write as my force is directly proportional to x and it is directed towards the mean position. But there is one very important point to note, is that this is an approximation. Why? Because if I pull the spring very hard, then this spring may break. So then there will be no force. It is no longer proportional to x. So this is valid only when x is small. So now if I remove this proportionality constant, I can write F is equal to minus kx. Let us try to understand what is this k. Is k dimensionless? Or dimensionful? And what does this k signify? It signifies. So I have pulled the mass and then it goes back and then comes. So like this it will oscillate. I would like to know what is this k. From this equation it is very clear that left hand side has units of force, and the right hand side, if I take my k dimensionless, then x has units of length. So this equation will be dimensionally incorrect. So in order to have this equation dimensionally correct, k should have dimensions of force per unit length. So one thing we understood, that k is dimensionful and it has units of force per unit length. Now another thing, that what does it actually signify? So for this let us try to do one more experiment. Now what will I take? I will take three different kinds of springs, okay, and then I will attach same mass m with these springs. One spring is big, one spring is small. So all the three springs are different. But I am attaching at present same mass, and also I am pulling the mass with same displacement x. So what will I observe? This mass will experience F1. This is equal to minus k1x. This will experience F2 minus k2x. And this will experience F3 minus K3 minus minus K3x. So I'm attaching same mass with all the three springs and pulling it with the same displacement. Now this information that these springs are different is going where? It is contained where? It is contained in K. This gives us the information that these springs are different. That is why we call this K as spring constant. Okay. So now we know something about K, and I have my force as F is equal to minus Ks. Now we will write down the equation of motion of the system. Okay. My force is F is equal to minus Kx. Okay. This force is for the mass spring system. Okay. Now we know, in order to write the equation of motion, we know from Newton's second law, F is equal to mass into acceleration. Okay. Here F is the force, mass, and A is the acceleration. Acceleration is defined as rate of change of velocity, and velocity I can define as rate of change of displacement. So this acceleration I can write as second order derivative of displacement, and here F is minus Kx. So I can write minus Kx is equal to mass into d2x by dt square. Okay. I will take my m on the left hand side, and then more neatly, if I would like to write this equation, I can write as d2x by dt square is equal to minus k by m into x. Okay. And now if I bring this to the left hand side, d2x by dt square is equal to this k by m I am writing as omega naught square. One important thing to note down here is that k is greater than 0 and m is greater than 0. So k by m is also greater than 0, and in order to have a positive quantity, I am taking this as omega naught square. So my omega naught square is k by m. So my differential equation, or my equation of motion for simple harmonic oscillator, comes out to be d2x by dt square plus omega naught square x is equal to 0. So this we got. Okay, nice. What actually omega naught is, we'll try to understand slowly. Okay. So now, after getting the equation of motion, my next goal is to find the solution of this equation. Okay. So what do we mean by the solution of a differential equation? Any mathematical function which will satisfy this equation will be the solution of this equation. Okay. So basically what we have got till now, we have a mass spring system or an oscillator which I have pulled. Now it is moving one side and then going to another, coming back, and then this motion is repeats after regular intervals. Okay. So for this motion I have my equation of motion, I have omega naught, but still I don't know how, or at, for example, at time t is equal to 1 second, 2 second, what will be my x? Okay. So basically I would like to know x as a function of t. Still that I don't know. So if I know that, then I know everything about my system. So this is our next goal, to find the solution or to find x as a function of t. So my next goal is to find x as a function of t. Now before doing any mathematics, let us try to visualize something. Okay, that once, so what are those things? We'll try to see without doing any mathematics. Now for this mass spring system, once this spring attached with a mass m is given to me, then k is fixed m is fixed. So my omega naught is fixed. Okay. This is fixed. Why? Because already we have seen that omega naught square is equal to k by m. Let me write this as k, which I have used earlier. Okay. Now, what else is there in my hand? You take this system and I pull the mass through some displacement. Now it is in my hand whether I pull here, here or more. So this is in my hand. Okay. So for example, and from where I am taking? From the unstretched mean position. So through here, whether I pull till here or I pull till here. So this is x1, x2. So this is in my hand. What do I choose? Right? This is my choice. And this we call as the amplitude. I give a name, amplitude. Okay. So this one is in my hand. Now is there anything else which is in my hand? So let us try to think. Here, for example, now you are doing this experiment with your friend. Okay. And this spring here, it is kept in an unstretched position, and this is my origin, my mean position. Now I have pulled this mass m through distance x. Okay. And your friend is holding a stopwatch here. Stopwatch. Okay. Simultaneously. Now, as soon as I leave this mass from here, here you start the stopwatch. So basically at time t is equal to 0. Then what will happen? This will, for example, this mass will come to the mean position in 2 seconds. It will go to the other direction around 2 seconds, come back in 2 seconds, 6 seconds, and come back here 8 seconds. So around approximately, for example, if it is taking 8 seconds to come back to its original position. Okay. And then it keeps on repeating the same motion. Now, for example, it is in your hands that you are holding the mass here at position A, and then when your friend, it starts the stopwatch at time t is equal to 0, you do not leave. And when 2 seconds are passed, then you leave it. That is also in your hands. So now there will be a difference. The motion will be the same, but there will be some difference from the previous situation. What this difference signify? This difference is called as phase. So this information of phase and earlier from what distance you are leaving the mass, that is at what initial displacement or distance you are leaving the mass, that information, and at what time you are leaving, this both the information should go in my solution, that is x at t, and these two you can choose. So another thing which you can choose is the phase. I hope you got the idea that what actually phase means. Okay. Now after having all this understanding, we can move further and then we can try to see what my solution can be. Okay. So these are the information which will go in the solution in x as a function of t. Omega naught, my amplitude, and the phase, in which amplitude and phase you can choose, and this will be your initial condition. Okay. Okay. So now let us try to write again the equation of motion which we got earlier. d2x by dt square, this is equal to minus omega naught square x. Okay. Let me give the name equation 1. Okay, where omega naught square is equal to k by m. Okay. Once the system is given, this is fixed. Now I need a mathematical function which, if you differentiate twice, you should get back that function itself and into omega naught square. So you can guess what that function can be. Okay. So if I take my x as a function of t as a cos omega naught t, then you can check that if you differentiate this, you will get minus sign, and then if you again differentiate that, you will get the function again with omega naught square. Okay. So this can be one solution. So you can write 1a. Okay. Now, so this you can check. For take the derivative and then try to check whether this satisfies equation 1 or not. Okay. Now, if I take xt as b sine omega naught t, you can easily check that this will also be the solution of equation 1. Okay. If you take the first derivative, second derivative, and then you check in equation 1, this will also be a solution. Now, if I take the combination of these two, a cos omega naught t plus b sine omega naught t. Okay. If I take the combination of these two, then I would like to give you an exercise to check whether this will also be a solution of equation 1. And you will see that when you substitute this in equation number 1, then this will also be the solution of our differential equation. Okay. And this is the most general solution. Okay. Okay. So we understood about some information we have, something we know about omega naught, and then amplitude and phase. And I am saying that this will be the most general solution, which we already saw from this equation. Okay. Now we will try to understand more deeply in our next video.